All right, here are solutions in a second. There we go. Here are solutions for the, I don't know, Thanksgiving practice worksheet quiz thing. Um, Going over sections, 4.2 and 4.3 in our book. So the basic idea here is I want you to be able to find and classify critical values and classify them two different ways using the first and second derivative test. So finding critical values, the important thing for you to know there is that critical values come in two flavors. They happen when your first derivative equals 0 and when your first derivative is undefined. So either way, I got to know what the first derivative is. Since I just have a polynomial here, it's pretty easy to figure out the first derivative. I'd get x cubed minus 3x squared minus 10x. And so I got to figure out when this thing equals 0 and when it's undefined. Well, it's never undefined because it's a polynomial. I'm not going to be dividing by 0 or taking square roots of negatives or anything like that. But it could equal 0. In fact, I'm going to have 3 spots where it equals 0. And I can find those by taking this thing and setting it equal to 0 and flexing some algebraic muscle. I might notice that each of my terms has an x in them, so I can start by factoring that out. And then what you're left with is a quadratic trinomial with leading coefficient equal to 1, and you can factor that. Just need two numbers that multiply to negative 10 and add to negative 3. So at negative 5 and positive 2 will do the trick. So now that I have it in its factored form, something times something else equals 0. That can only happen if one of those things equals 0. In other words, the x is 0, the x minus 5 is 0, or the x plus 2 is 0. So either x is 0, or x is 5, or x is negative 2. These are my three critical values. But it's not enough to just find the critical values. What I want you to do in this worksheet is to classify those critical values. And in fact, I want you to do it twice. So when you classify critical values using the first derivative test, you can kind of start with a number line here and divide your number line up into regions according to your critical values. So negative 2, 0, and 5, if I kind of plot those on a number line, that divides my number line up into 4 different regions. And so all I got to do is test a number from each of the regions. So if I test a number in region 1, any number that's less than negative 2, so maybe negative 3. What I mean by test is plug it into your function and figure out if the output is positive or negative. I could plug that in up here, but then I'd have to figure out what negative 3 cubed is. Not that bad, but I'd rather not. I'd rather plug it in down here into the factored form of this polynomial. Because I don't need to know what the number is, I just need to know what the sign is. So when I change all the x's into negative 3, this is negative, this would be negative, negative 8, and this would be negative, negative 1. And a negative times a negative times a negative gives me a negative. So f of negative 3 is equal to some negative number. In other words, when I'm in region 1, the sign of my first derivative is negative. I can pick any number in region 2, maybe negative 1, for example. If I plug that in down here, if I plug in negative 1, I get a negative, and then a positive. A negative times a positive gives me a positive number. So the sign of my first derivative in region 2 is positive. Pick any number in region 3. I don't know, 1 maybe. Go through the same analysis. Positive, negative, positive. So that gives you a negative. So the sign in here is negative. And then finally pick any number in region 4. I don't know, 10 maybe. Positive, positive, positive. Positive times a positive times a positive is a positive. So in region 4, my first derivative is positive. Now that I have this sign line, which is what this is called, I can classify my critical values. At negative 2, the sign of my first derivative switched from negative to positive. So if you want to picture it, my graph was decreasing, then it hits negative 2, and then it starts increasing. What that tells me is that negative 2 is a local minimum. Similarly, at 5, my graph was decreasing, then it starts increasing. So 5 and negative 2 are, I shouldn't do that, that's just sloppy. 5 is also a local minimum. However, at 0, my first derivative switched from positive to negative. So my graph was going up, it hit 0, then it starts going back down. Sounds like a local max to me. So 0 is a local max. I've classified all my critical values, so in a sense we're done. But what I asked you to do is kind of confirm your answers or confirm that you understand the second derivative test by coming up with these same answers a different way. And the different way is to find the second derivative. So if the first derivative is x cubed minus 3x squared minus 10x, the second derivative would be 3x squared minus 6x minus 10. In the second derivative test, I don't test numbers around my critical values. I test the critical values themselves. So I figure out f double prime of negative 2. And again, it doesn't matter what the number is. It just matters whether that number is negative or positive. So negative 2 squared is 4. And 4 times 3 is 12. And then negative 6 times negative 2 is also 12. 12 and 12 gives me 24. So even when I subtract 10, I'm still going to be a positive. So f double prime of negative 2 is positive. Similarly, f double prime of 0, my next critical value, will change all the x's into 0. 0 minus 10 gives me a negative. And f double prime of 5. 5 squared is 25 times 3 is 75, which is enough positive that I won't get negative by subtracting 30 and 10 more. It's a weird way to say that. My point is that f double prime of 5 is a positive number as well. F double prime of negative 2 is a positive number. What that tells me is that my graph is concave up when I'm at negative 2. If you picture concave up, the point where the first derivative equals 0 in a region that's concave up would look like a local minimum. So this tells me that negative 2 is a local min. Same conclusion I had over here. This tells me that 0 is a local max. And that's because the second derivative is negative. That means my graph is concave down. And if you picture a concave down region, the spot where the first derivative equals 0, the spot where it's flat, would be a local maximum. And for the same reason that negative 2 is a local max, positive 5, or is a local min, positive 5 is a local min. So we come up with the same conclusion, we just got there a different way. We use the second derivative test. Part D here, I don't know, I'm not going to do it. You're supposed to sketch a graph of f prime, and f double prime. Yeah, you can do that. Plug it into a calculator. Great, you get a graph. Why? Why did I make you bother doing that? Well, I guess I thought that that might add some understanding for you. You could kind of look at your first derivative and see that it's negative and then positive and negative and then positive. You could look at your second derivative and think about the sign of it. You could think about the graph of your function and its critical values and what you know about the first and second derivatives at those points or around those points, and kind of understand these tests a little bit more deeply, maybe. Or maybe that was all wishful thinking. I don't know. Get as much or as little out of D as you want. I trust that you guys can graph things as you want. And so I'm not even going to bother graphing it because I don't want to graph it. I want to end this video right now. Wish you a happy Thanksgiving, and I'll see you when we get back.